Okay, elastic and inelastic collisions. This really takes conservation of energy and conservation of momentum and combines them together. So when any two objects collide, we're going to take a look at the momentum and energy before and after that collision. So in terms of the energy, if the kinetic energy before the collision is the same as the kinetic energy afterwards, we say that it's an elastic collision. Now, in the real world, a lot of that energy will be converted into other types, so heat and sound. And for those types of collisions where some of the energy is lost, meaning it's converted into heat or sound, that's an inelastic collision. And in the real world, most of our collisions are inelastic. If we take a look at collisions, though, at the subatomic world involving particles where they don't actually come into contact, like electrostatic repulsion, things like that, or even gravitational interactions when we send a satellite out through the solar system, and the gravitational interaction between it and other planets would also be considered an inelastic collision, even though they're not colliding. But most real-world collisions are inelastic. We know that there's going to be some heat or sound energy, so some of that kinetic energy gets converted into heat or sound. So for any collision, we now know that there's two basic principles that we're looking at. The initial momentum is equal to the final momentum, and then we're also going to look at the kinetic energy. Is the kinetic energy before the collision equal to the kinetic energy after the collision? If it is equal to them, the kinetic energy before is equal to the kinetic energy afterwards, we can say it's an elastic collision. So for the most part in grade 12 physics, that's as far as you're going to be asked to go. You'll do basic conservation of momentum questions on an interaction. And then there will be a part B which will say, is this an elastic or inelastic collision? And you're just going to compare the kinetic energy. Now the textbook does take these two equations and combines them together. So substitutes one equation into the other equation, and through a lot of math, they come up with basically that the initial velocity of object 1 plus the initial velocity of object 2 has to be equal to the final. Now this equation, even though it appears in the textbook, doesn't appear on our formula sheet, so you can't actually use this one. Okay? I find a lot of students memorize this or they write it down somewhere and then they start off in a question using this. Again, I'm more interested in how did you get to your final answer. And by taking this equation, you kind of skipped out all of the physics involved in the conservation of momentum and conservation of energy and setting them equal to each other because it's an elastic collision. And basically you're just plugging numbers into an equation, and that's not really physics. Okay? So don't write down this equation. I know it's in the textbook, but it's not a principle of physics. Okay, it's just a byproduct of these two principles when you combine them together. So you can't actually start from here. Okay, another place where you might actually use conservation of momentum and conservation of energy is in this object here, which is called a ballistic pendulum. Kind of looks like a pendulum, so we have this one mass. Usually it's something like a block of wood or something like that, and another object, like say a bullet fired from a gun. And what we're trying to find is how fast is this bullet traveling, right? So we want to know what is the speed of the bullet. Well, when the bullet hits this block of wood, it becomes embedded in the block of wood. So we can see here the two masses are combined. And the block of wood, because it's attached to this rod, will swing up due to conservation of energy, right? The bullet combines here, so we have conservation of momentum first, right? So we have the bullet traveling at some initial speed, and this object has no momentum. And then afterwards, we have the block of wood and the bullet traveling at some new speed, right? So the conservation of momentum here, the initial momentum, which is just the bullet, the final momentum, which is the combined mass. So if we know the two masses. Obviously, those are things that we can measure in the lab. If we could find this velocity here, the velocity of the pendulum, we could then determine the initial velocity of the bullet. How fast was the bullet traveling when it struck the pendulum? Now, what we're going to use is conservation of energy to find that final velocity. So we know that the kinetic energy that it had here at the bottom of the swing gets converted into potential energy up here. So again, now we can say the kinetic energy of the pendulum, all of that kinetic energy gets converted into potential energy afterwards. Sorry, this is the combined mass. So basically, by measuring the height that the pendulum travels upwards, we can find the velocity that the pendulum started with, and using that velocity, we can find the velocity of the bullet. Okay? So again, we're using conservation of momentum and conservation of energy in the same question. Okay? All right, so those are the two examples of where you'll use those two laws, at least in Physics 12. And if you have any questions, you can ask me in class.